So you might know about the overlapping clock hands problem, which asks a very simple question. If the minute hand and the hour hand of a clock are exactly overlapping, how much time is going to pass until they're exactly overlapping again? The answer to this problem, however, can be very simple to quite complicated, depending on your approach. I'm going to present 4 different ways of solving the problem, and I'd like to start with the most elegant one. Alright, for our first method, we simply ask ourselves, how many times will the hands overlap in a 12-hour interval? We will now start the clock and we'll be able to count the overlaps. If you have a clock or watch in hand that you can manipulate, feel free to try this out for yourself. Okay, I counted 11 overlaps within 12 hours. Note that when it's 12 o'clock again, we must not count that overlap if we already counted the overlap at 12 o'clock at the beginning. Since the 11 overlaps are evenly spaced, the time between 2 overlaps equals 12 over 11 hours, which is about 1 hour, 5 minutes and 27 seconds. For the next methods, we need a way to measure the angle that the hands have moved since 12 o'clock. I will use a system where 1 complete turn equals an angle of 1. Half a turn equals an angle of 1/2, and so on. This makes the following calculations most compact. We can now introduce the angle that the hour hand has moved, and I'll denote it by lowercase phi. Lowercase omega stands for the hour hand's angular speed. I do the same for the minute hand using uppercase letters, and of course the minute hand is 12 times as fast, completing a turn in an hour. Now the second way to calculate the time between overlaps is to use the relative angular speed delta omega of the clock hands. They move apart at 11 over 12 per hour. Note that when they are a number of full turns apart, they're actually overlapping again, so we set the relative angle delta phi to any natural number. To obtain the smallest non-zero interval, we set n to 1, and we find that t equals 12 over 11 hours again. Okay, the third method is a little more brute force. I remind you that we imagine our clock starting at 12, and now we're going to count the time to the next overlap. Fast forward 1 hour and the minute hand will be at 12 again, while the hour hand has moved to 1. We note that 1 hour has passed. Now the minute hand needs to catch up, so we allow it to move an angle of delta phi equal to 1 over 12 to get where the hour hand currently is. This takes 1 over 12 hours, and we add that to our time total. The hands do not overlap though, since meanwhile the hour hand has moved a bit forward as well, by delta phi equals omega times delta t, which is 1 over 12 squared. Now in order to catch up, the minute hand has to travel this additional angle, which takes delta t equals delta phi over omega equals 1 over 12 squared hours. So we add that to our time total, and we start to see a pattern. If we were to go through another iteration of this, we would find a term with a power 3, and so on. We can therefore write the time as an infinite series. If we did everything correctly, this series needs to converge, since the clock hands do overlap in a finite amount of time. And in fact, it does. It is a simple case of the geometric series, and there is a formula for it. This is the most general expression, and it is true for any r that isn't 1. Now in our case, a is 1, r is 1 over 12, and n goes towards infinity. Since r is smaller than 1, r to the power n vanishes as n goes to infinity, and we're left with 1 over 1 minus 1 over 12 hours, which is exactly 12 over 11 hours again. For the fourth method, we simply state that the angle traveled by both hands has to be the same for them to overlap. I think this is actually the most intuitive approach, but I also think it is the worst way of solving the problem. Anyway, it yields an equation for t that seems contradictory at first. T over 12 hours equals t over 1 hour. There is no contradiction, however, if we look at how the angle works for values greater than 1. 1.5 turns, for instance, are equal to a half turn, and so are 2.5 turns, and 3.25 turns are actually just a quarter turn. For our equation to reflect that property, we need to apply a function on both sides that satisfies f of x is f of x plus 1, a periodic function with period 1. We are not limited to a period of 1, however, since we can just multiply the equation by any constant and apply a periodic function whose period equals that constant. The obvious choice here is 2 pi, and the functions we're going to use are a sine and cosine function. You can think of the effect the periodic function produces as if we took the number ray, cut it off at 2 pi, and formed a circle out of it. So we have our equation multiplied by 2 pi, and we're going to apply the sine function to both sides and the cosine function to both sides. We can now plug these equations into a computer algebra system to obtain numerical solutions. We're looking for the smallest non-zero value of t that satisfies both equations. If we only look at one equation, we get solutions to the equation that are no solution to the clock hands problem, and I think this is because sine and cosine are not only periodic, but have other symmetric properties as well. Nevertheless, only accepting values for t that satisfy the sine and the cosine equation, we find the lowest non-zero value to be a decimal number that corresponds to the previously obtained solution 12 over 11 hours. This shows that the same problem can be easy or rather complicated depending on how you look at it. Often, the most elegant approach requires you to think some time about the problem before getting started, but it can be extremely rewarding to do.